Dynamic programming. I'm Evina and I'll be presenting you this topic. The topics of discussion in this presentation are: what is a dynamic programming, what is principle of optimality, and 3 problems using the principle of optimality to find its solutions. They are the coin-row problem, the Warshall's algorithm, and the Floyd algorithm. What is dynamic programming? Dynamic programming is a technique for solving problems with overlapping subproblems. Dynamic programming suggests that solving each of the smaller subproblem only once and recording the results in the table would lead to the solution to the problem. For example, consider calculation of Fibonacci numbers, which is given by the relation f of n equals f of n minus 1 plus f of n minus 2. It could be noticed f of n is expressed in terms of its smaller and overlapping subproblems of computing, which are the f of n minus 1 and f of n minus 2. The calculation of Fibonacci numbers proceeds with the record of the values of the last 2 elements in the Fibonacci sequence to find f of n for n greater than or equal to 3. Principle of optimality. The principle of optimality states that an optimal solution to any instance of an optimization problem is composed of optimal solutions to its sub-instances. In this presentation, we'll discuss 3 examples that uses principle of optimality. They are the coin-row problem, the Warshall's algorithm, and the Floyd's algorithm. The coin-row problem. The coin-row problem statement states that there is a row of n coins whose values are some positive integers c suffix 1, c suffix 2 to c suffix n, which may not be necessarily distinct. The goal of the problem is to pick up the coins that results in maximum amount of money. The coin-row problem has a constraint, that is, no 2 coins adjacent in the initial row can be picked up. The coin-row problem could be represented using the recurrence relation f of n equals max of c of n plus f of n minus 2 or f of n minus 1 for n greater than 1. And the initial values are considered as f of 0 equals 0 and f of 1 equals c suffix 1. Let me illustrate the coin-row problem with an example. In the coin-row problem, the coins are arranged in a row. In this example, the coins arrangement are represented by the array C, which consists of coin with values 5, 1, 2, 10, 6 and 2 occupying subsequent indexes of array C and which are represented in these tables. In the coin-row problem, to find the coins with the maximum total value, backtrace the computation to see which of the 2 possibilities produce the maxima. The 2 possibilities are c suffix n plus f of n minus 2 or f of n minus 1, where the function f represents the maximum total value in the coin-row problem. In the first iteration, considering f of 0 equals 0, f of 1 equals c suffix 1, which equals 5. In the second iteration, considering f of 0 equals 0 and f of 1 equals phi, f of 2 equals max of c of 2 plus f of 0 and f of 1. The maximum is the f of 1 value, which equals phi. Calculating f of 3, which will be equal to max of c of 3 plus f of 1 and f of 2. The maximum is c of 3 plus f of 1, which is 5 plus 2, which equals 7. Calculating f of 4, which is max of c suffix 4 plus f of 2 or f of 3. Here c suffix 4 equals 10 and f of 2 equals 5, which is the maximum value. 10 plus 5 equals 15. Calculating f of 5, which is c suffix 5 plus f of 3 and f of 4, which equals 15. Here the maximum value is f of 4, which is 15. In the last application of the formula, it was the sum c suffix 6 plus f of 4, which means that the coin c suffix 6 equals 2 is part of an optimal solution. Hence, backtracing to the computation of f of 4, the maximum was produced by the sum c suffix 4 plus f of 2, which means that the coin c suffix 4 equals 10 is part of an optimal solution as well. Finally, the maximum in computing f of 2 was produced by f of 1, implying that the coin c suffix 2 is not the part of an optimal solution and the coin c suffix 1 equals 5 is part of the solution. Thus, the optimal solution to the coin row problem is the set c suffix 1, c suffix 4 and c suffix 6. Here is an algorithm for the coin row problem. The algorithm receives an input array representing the row of coins as input. The array values are positive integers. The output of the algorithm is the maximum amount of money that could be picked up from these row of coins, considering the constraint of the coin row problem. F of 0 is initialized to 0 and f of 1 is initialized to c of 1. Then iteratively f of I is calculated as maximum of c of I plus f of I minus 2 and f of I minus 1. The last value f of n holds the maxima for the coin row problem. The time complexity of the coin row problem equals theta of n. Warshall's algorithm. It finds the transitive closure in a directed graph. The transitive closure of a directed graph with n vertices can be defined as a n cross n Boolean matrix T equals T suffix ij, in which the element in the ith row and jth column is 1 if there exists a non-trivial path from the ith vertex to the jth vertex. otherwise t suffix ij is 0. Let me illustrate the transitive closure with the given directed graph as example. The directed graph consists of 4 vertices A, B, C and D with directed edges between them. The matrix A represents the adjacency matrix, which has a value of 1 when there is a directed edge between the vertices. For example, there is a directed edge between the vertex A and vertex B. Hence, the value is 1 in the corresponding position of the Ath row and Bth column. There is a directed edge between the vertex B and the vertex D. Hence, there is a value of 1 in the adjacency matrix A in the location of Bth row and Dth column. And similarly, there is an edge between the vertex D and vertex A. Hence, there is a 1 in the Dth row and the Ath column. Similarly, there is an edge between the vertex D and vertex C. Hence, the adjacency matrix has a value of 1 in the Dth row and the Cth column. From the adjacency matrix, the transitive closure matrix T could be derived. The transitive closure matrix T represents the presence of a directed path between the vertices. For example, there is a directed path for A to itself. That is, A has a directed edge to B, B has a directed edge to D, and D has a directed edge to A. Hence, in the transitive closure matrix T, there is a 1 in the Ath row and the Ath column. There is a directed edge from A to B, and hence in the transitive closure matrix in the Ath row and the Bth column, it has a value of 1. There is a directed path from A to C, which is from A to B there is a edge, from B to D there is a edge, and D to C there is a edge. Hence, there is a path from A to C. Hence, in the transitive closure matrix, there is a 1 in the Ath row and the Cth column. And there is a path from A vertex to the D vertex, which is A to B, there is a directed edge, and B to D, there is a directed edge. Hence, there is a directed path from A to D, which is represented by 1 in the Ath row and the Dth column. Similarly, the path between the vertices in the directed graph is calculated from the adjacency matrix and stored in the matrix T, which is the transitive closure of a directed graph. Let me explain how this transitive closure T is derived from the adjacency matrix A. Warshall's algorithm finds the transitive closure matrix from the adjacency matrix iteratively. Each iteration in Warshall's algorithm finds a matrix that represents the existence of path with corresponding number of directed edges. For example, At the first iteration, the matrix R0 represents the adjacency matrix with a value of 1 at the ith row and the jth column if there is an directed edge from the ith row and the jth column. In the next iteration, the matrix R2 consists of value 1 at the ith row and the jth column if there is a directed path of length 2 between the ith row and the jth column. And at each iteration, the matrix is generated using the formula R of k suffix ij equals R of k minus 1 suffix ij or R of k minus 1 suffix ik and R of k minus 1 suffix kj. So, considering the generation of matrices R0, R1, R2, R3 and R4 for the given directed graph, the ones in R0, as I said earlier, represents the existence of a directed edge between the vertex. The boxed row and column in R0 is used for getting R1. That is, there is a 1 at the eighth row and the bth column, and there is a 1 at the dth row and eighth column. Hence, finding the AND between these values, at R1, the value at the dth row and the bth column is 1, which represents there is a path of length 2 between D and B. We could verify that in the graph. That is, B has a directed edge from D to A, and there is a directed edge from A to B. Hence, there is a path from D to B of length 2. Similarly, R2 is generated from R1. The boxed row and column are used for getting R2. In R2, the ones represents the existence of path with intermediate vertices numbered not higher than 2. The boxed row and column are used for getting R3. In R3, ones reflect the existence of path with intermediate vertices numbered not higher than 3. The boxed row and column are used for getting R4. R4 is the transitive closure of the given directed graph. The ones reflect the existence of path with intermediate vertices numbered not higher than 4. Thus, the Warshall's algorithm finds the transitive closure matrix from the given adjacency matrix. Warshall's algorithm receives the adjacency matrix of a digraph with n vertices as input. The output of the Warshall's algorithm is the transitive closure of the digraph. R0 is initialized with the adjacency matrix of the digraph. Using for loops, Rk of ij is assigned the value R k minus 1 of ij or rk minus 1 of ik and rk minus 1 of kj. The algorithm returns the transitive closure of the digraph. The time efficiency of the Warshall's algorithm is theta of n cube, and the space efficiency could be obtained by overwriting the matrices that are generated in the preceding iteration. Floyd's algorithm. In a weighted digraph, Floyd's algorithm finds shortest path between every pair of vertices. Floyd's algorithm uses the same idea as Warshall's algorithm to find all pairs' shortest path. That is, Floyd algorithm constructs solution through a series of matrices D0 to Dn using increasing subset of vertices allowed as intermediate. Consider the example digraph given here, which consists of 4 vertices A, B, C and D. The edge connecting the vertices has a weight associated with it. The matrix W represents the edge between the vertices in the digraph. For example, there is an output edge from vertex A to vertex C with a weight associated with it, which is 3. Hence, at the eighth row and the cth column in matrix W, the value is 3. The vertices in the digraph does not have a self loop. Hence, along the diagonal of the matrix W, the values are 0. There is no outbound edge from A to B or D. Hence, the value at Ath row, Bth column and Ath row, Dth column is infinite. So, similar to this, all the values in the matrix W is allocated. The matrix D represents the existence of a path between the vertex, and the value at the corresponding location at matrix D represents the weight of the shortest path between the vertices. For example, between vertex A and B, there is a path from A to B through C. That is, A has an outbound edge to C with a weight 3 and C has an outbound edge to B with a weight 7. Hence, the total weight from A to B is 10, which is represented in the Ath row and the Bth column value 10 in the matrix D. Similarly, all values in matrix D represents the weight of the path between the corresponding vertices. How would we derive the matrix D from matrix W? Let's use the Floyd's algorithm. In Floyd's algorithm, D0 is initialized with the weight matrix W. The weight matrix W consists of the weight of edges between the vertices in the digraph. At each iteration, the matrix dk is generated by considering the minimum of the values in the matrix D of k minus 1 or the sum of the intersecting values at D of k minus 1. For example, for the given digraph, D0 represents the length of the shortest path with no intermediate vertices. D1 is generated from D0 considering the first row and the first column. The value at D1 is equal to the minimum of the values at D0 or the sum of the intersecting values at the first row and the first column of D0. For example, at D0, the intersecting value at B row and C column is infinite. But the sum of the intersecting value at the first row and the first column is 3 plus 2, which is 5, which is less than infinite. Hence, at D1, at the bth row and the cth column, the value is 5, and similarly, the value at dth row and the cth column is 9. Hence, D1 represents the length of the shortest path with intermediate vertices numbered not higher than 1. Similarly, D2, D3 and D4 are generated from the previous iteration D matrix. And D4 represents the length of the shortest path with intermediate vertices numbered not higher than 4. The pseudocode for Floyd's algorithm is as given here. The input to the Floyd's algorithm is the weight matrix W of the graph with no negative length cycle. The output of the Floyd's algorithm is the distance matrix of the shortest path lengths. The matrix D is initialized with the weight matrix W. Using nested for loop, Dij is assigned the value as minimum of D of ij or the sum of the values D of ik and D of kj. The time efficiency of Floyd's algorithm is theta of n cube, and the space efficiency is obtained by generating matrices that overrides the predecessors. To summarize, in this presentation we discussed the dynamic programming, which is a technique for solving a problem by recording the results of its subproblem. We discussed the principle of optimality and 3 examples that applies principle of optimality, which are the coin row problem, the Warshall's algorithm and the Floyd's algorithm. Thank you.